All right, so we're going to review many factoring techniques. Factoring is one of the most valuable skills we will use during this course, and it's going to be used in a variety of situations. I will tell you right now, factoring is not just used to solve equations, so you cannot just say, oh, well, I know the quadratic formula and that is good enough. You also cannot just rely on a calculator in certain situations, because again, there's situations where we need to be able to factor without solving or without something that a calculator can handle for us. So, I'm going to review with you several common forms of factoring, starting with what are called perfect squares. A perfect square is, once it is factored, it is a square. So something like a plus b squared or a minus b squared. If you FOIL these out, what you get is these. Now, of course, for factoring, we're going to be looking at going backwards on them. So we need to be able to recognize the right-hand side and turn it into the left-hand side. So for our first example, x squared plus 6x plus 9. All right, so first of all, there is a plus on the middle term, so if it is a perfect square, it will be the top kind. The first term must match a squared. That means my a in this example is x. The last term must match b squared. That means my b in this example must be 3. And then the big thing to determine if it is a perfect square is if the middle term turns out to be what it should be, which is twice a times b. So 2 times x times 3 does in fact equal 6x. This is a perfect square. Okay, and therefore it will factor as x plus b quantity squared. Now, this example in particular might have been easier for you to factor with a method we're going to review a little bit later on, but what happens often is that we are looking at perfect squares in much more complicated situations where it really will save you time if you can recognize that they are perfect squares. So when I look at this and need to factor it, the first thing I realize is that both 16 and 49 are perfect squares. So I'm not yet sure if the entire thing is a perfect square, but because of the 16 and the 49, I'm going to check. So a would have to be 4x, b would have to be 7, and again, it's the middle term that decides if it really works. It is a minus sign, so it would be the bottom one. Okay. 2 times 4x times 7 does in fact equal that 56x. So this is in fact a perfect square, and it will factor as 4x minus 7 quantity squared. This is significantly shorter than the method we will have for dealing with quadratics with numbers in front of the x squared later. All right, now this was a very specific circumstance. So is the next one, only it happens to be a circumstance that shows up way more often than you'd expect, especially when we get to trigonometry. So a difference of squares starts out exactly like it says. It is a difference of two perfect squares. So it is a lot easier to recognize than a perfect square. And it will factor as a plus b times a minus b. So starting with x squared minus 9 as our first example, it is a difference of two things that are perfect squares. In this case, a is x and b is 3. So it will factor as x plus 3, x minus 3, and I'm done. Okay. Now my next one is not a difference of squares as written, but it illustrates something that is often forgotten with factoring, in that the very first thing you should always do with factoring is ask yourself if there's anything that can be pulled out of all of the terms. And in this case, there is. Both terms have a y, and I can factor out the y. I can't get rid of it. It's going to stay right where it is for the rest of the problem. But I can factor it out and then basically ignore it. Now, the part that is left in the parentheses is, of course, a perfect square. A is 4x squared, b is 9. So what do I get? Well, I still have the y, and then I get a plus b and a minus b. Now I'm not done. Y, of course, is as simple as I can make it. 4x squared plus 9, nothing can happen with. Okay. It is a fact with factoring that when you have only two terms like this, 4x squared and 9, if it is a plus in the middle, absolutely nothing you do will factor it. But the second term here, 4x squared minus 9, is another difference of squares. For this one, a is 2x and b is 3. So I still have the y, I still have the 4x squared plus 9, but the 4x squared minus 9 then becomes 2x plus 3, 2x minus 3. And now absolutely nothing can be done. Okay. By the way, this, and this are all what we call linear terms, meaning they have no exponent in them, can't be factored further. And again, a term with only a factor with only two terms in it and a plus in the middle can also never factor. Okay. All right. Moving on. We are going to factor what are called monic quadratics. So a quadratic is a term with an x squared in it, and monic means there's nothing in front of the x squared. Okay. So this will factor as x plus something I'm going to call s times x plus something else I will call t. This is one of those where you can literally write down the answer because all the work is done in your head. So how do you find s and t? S and t need to be two numbers so that they add to this b in the middle and they multiply to the c here. Since there are fewer ways to multiply to something than add, I usually start actually with the multiplication and then pick which ones I want based on the addition. There will never be more than one possibility for s and t that fit both situations. Okay. And it's just a matter of being careful, especially if there are negative signs in place. So for our first example, I need two numbers that multiply to positive 6 and add to negative 5. All right, so first of all, to multiply to 6, your choices are 1 and 6 or 2 and 3. To multiply to positive 6, either both numbers need to be positive or both need to be negative. Since they need to add to negative 5, they in fact both need to be negative. And then I say which of these pairs add to negative 5, and the answer is, of course, negative 2 and negative 3. So x minus 2, x minus 3. Okay, x squared minus 2x minus 8. Again, I'm looking for two numbers that multiply to negative 8 and add to negative 2. So multiplying to 8, ignoring the negative sign for right now, is 1 and 8 or 2 and 4. To multiply to a negative number, one of them but not both needs to be negative. So my question then becomes, which of these, when one is negative and one is positive, add to negative 2? It is, of course, the 2 and the 4, and to add to negative 2, the 4 has to be negative. So this becomes x plus 2, x minus 4. All right, one more. X squared plus 8x plus 12. So this time I'm looking for two numbers that multiply to 12. They can be 1 and 12, 2 and 6, or 3 and 4. Because it is a positive 12, they're either both positive or both negative. Since they need to add to negative 8, they're both positive, and my answers are 2 and 6. So it factors as x plus 2, x plus 6. Okay. Next, we are going to do a technique called factoring by grouping. Now, factoring by grouping is one of the few ways that we can deal with factoring things with a degree higher than 2. So like a cubic or a quartic. But they're also going to be helpful for degree 2 equations. So, first of all, to proceed to factor by grouping, I need an even number of terms, most often 4. So, I have 4 terms. I'm going to group them 2 and 2. Now, in my first grouping, I say, what does this grouping have in common? My answer is x squared, and I factor it out, and I'm left with x plus 3. In my second grouping, I say, what does it have in common? I say 4. Only I'm going to pull out a negative 4 because I always want to be left with a positive for my first piece. And here I'm again left with x plus 3. Now this is the point where you will know if factoring by grouping will actually work. Because for factoring by grouping to work, the leftover piece from both groups must be identical. It is. So then the x plus 3 can be factored out, and what I'm left with is x squared minus 4. Now I'm not done. X plus 3 is of course linear, cannot factor further, but x squared minus 4 is quadratic, so potentially could. And because there's only two terms and it's a minus sign, I'm hoping it's a difference of squares, which it is. So it becomes x plus 2, x minus 2. Okay, once again, I have four terms, which is not only required for factoring by grouping, but is usually a big hint that that's what you should do. In my first group, I can pull out a 2 and an x squared and be left with x plus 3. In my second group, I can pull out a 5 and be left with x plus 3. The leftovers are identical in both pieces, so it gets pulled out, and I'm left with 2x squared plus 5. 2x squared plus 5, again, only two terms and a plus in the middle. Nothing can factor that. Okay. All right, so now that we know how to factor by grouping, I'm going to return to general quadratics. That is quadratics with a number in front of x squared. And I'm going to do something called the AC method. Now, a lot of people are taught a method that is essentially guess and check for this. And personally, I despise guess and check in all situations. That may be because I'm an absolute horrible guesser. But mostly it's because I don't like the idea of guessing and checking, that you're blindly searching around for answers. I like a method, even if sometimes it takes longer, that I know will get me there eventually, and will also be able to tell me if it's not going to work, as opposed to me just wondering, did I not guess the right thing? So, I prefer the AC method. Now, the AC method, again, is for quadratics with a number in front of x squared. As the name implies, what I'm going to do is I'm going to take the a term and the c term, in this case 4 and negative 3, and multiply them to get negative 12. Now, I need two numbers that multiply to negative 12 and add to negative 1, which is that number from the middle. You see the similarities to Monic quadratics. To multiply to 12, I need 1 and 12, or 2 and 6, or 3 and 4. To add to negative 1, it's going to be this one with a negative sign on the 4. Now, unfortunately, unlike in Monic quadratics, and I cannot just write down my answer here. What I do now is take this minus x and break it apart into a plus 3x minus 4x from these two numbers. Now, what this did is turned what looked like something with 3 terms into something that has 4 terms, which means I can factor by grouping. Now, when we were learning factoring by grouping, I said that once you had actually factored each group, you had to have the same thing in them, and that's what told you if it would work. With AC method, if you picked the 3 and the negative 4 here correctly, it will always work. So if we get to that step in the factoring by grouping and the pieces and the parentheses are not the same, we know we picked the wrong numbers. So in this one, I can factor an x out, and I'm left with 4x plus 3. Negative 4x and negative 3 have nothing in common, but I'm always going to pull out the negative sign to be left with 4x plus 3. The 4x plus 3, of course, is in common, and I'm left with x minus 1. Okay. All right, next example. This time, to do AC, I take 2 times 6, and it gives me 12, positive 12 this time. Okay. I want them to add to positive 7, so it is again the 3 and the 4, only this time both are positive. So I'm going to break the 7x apart as plus 3x and plus 4x. A commonly asked question is, does it matter which order I wrote the 3 and the 4? The answer is no. Your work will look different for 2 steps, but your answers should be the same. So, grouping now. Out of the first 2, I can pull an x and be left with 2x plus 3. Out of the second 2, I can pull a 2 and be left with 2x plus 3. I then pull out the 2x plus 3, and I'm left with x plus 2. Okay. I'm going to do one more of these. A times c this time is negative 8. So that's 1 and 8, or 2 and 4, with one of them being negative. To make a positive 7, I'm going to need the 1 and the 8, and the negative will be on the 1. So this will break apart as 2x squared minus x plus 8x minus 4. And then I will group. I can pull out an x and be left with 2x minus 1. I can pull out a 4 and be left with 2x minus 1. Pulling out the 2x minus 1, I'm then left with x plus 4. All right, there is one thing left with factoring, and that is a way of factoring higher degree things when grouping won't work because I don't have enough terms. So this is called difference or sum of cubes. So, unlike with squareds, you can actually factor whether it's a plus or a minus. Okay. Now there is a pattern with these. The first term takes its sign from the original, so if it was a minus, it's still minus. If it was a plus, it's still plus. And I'm taking the cube root of each one. The second term is always derived from this. Square the first term, change the sign, multiply the a and the b, square the last term. Square the first term, change the sign, multiply a and b, square the b. Okay, these are quadratics, but they are quadratics that should never factor. All right, so x cubed minus 27. Okay, obviously a is x, and the cube root of 27 is 3. It is a minus sign, so I'm in the first case. So it will factor as x minus 3, x squared plus 3x plus 9. Again, I said that that second term should never factor. It is a monic quadratic, so if I were going to factor it, I'd need 2 numbers that multiply to 9 and add to 3. The only numbers that multiply to 9 are 1 and 9, or 3 and 3. Neither case do I add to 3. Okay, a little bit more complicated one. So you're like, that's not a cube. That's okay, it doesn't have to be. Okay, it is a plus, so I'm going to be in the middle case. The cube root of x to the 6th is x squared. The cube root of 64 is 4. So this becomes x squared plus 4, x to the 4th minus 4x squared plus 16. Okay, I already know the second one won't factor. The first one won't factor because it's a plus as opposed to a minus inside it. And as we know, those don't factor.